Again, welcome to Biostatistics. In these lectures, we're going to study how to compare independent means. In our previous lectures, we went through dependent means, how to compare two dependent means. And we use the term paired. So a paired and independent samples means dependent and independent sample. Also, exploratory and descriptive statistics. Inference about the main difference. Now we have two samples. So we're going to learn how to find the main difference of it. Also, equivalence T procedure, conditions for inference, and sample size and power. Actually, the sample size and power for independent sample is the same procedure as we did for both single sample and dependent sample in our previous lectures. So again, the formula is the same, the concept is the same. So we are not going to cover it here. But the reason why I put that as an objective is just to bring the note out that, again, to find the sample size or the power of a test, we use the same formula as for dependent sample as independent sample. Is the same formula in the same process. So first we start with different types of sample. That is the sample type for comparing means. Again, we have a single sample. A single sample means we have only one group, no concurrent control group. There's no comparison made to external population. We cover this in unit 11, that's chapter 11 of the course textbook. So a single sample normally reflects the experience of a single group. No concurrent control group is present, but the result may be compared to previously established norms or expected values. Again, the previous lectures we covered this. The next is the pair samples. A pair sample is we have two samples with each data point, one sample uniquely matched to a point in other sample. So a pair sample is more or less like you have two dependent samples. The size of each sample must be the same because each value is point to another. So how do we get a pair sample? I'll give the same example we did in the previous lectures. For example, in a golf game, we need a golf club. When I buy a golf club newly, maybe there was a claim by the manufacturers that a new golf club gives us a better score than old golf club. So what I will do, I'll buy a new golf club, I will use it and record the data, the score and performance of it. Then let's say after 2 months it's old, I will use the same golf club and get the same amount of data and the scores. Now I'll compare the two. This is dependent variable. The reason why, because we are using the same golf club. Now, if I'm using two different golf clubs, then it becomes what we call the two independent samples. So a pair samples use data from two samples in which each data point in the first sample is uniquely matched to a data point in the second sample. And a pair sample analysis was again discussed in our previous unit 11. Now, this is the first time we will go through two independent samples. So that will be totally two separate groups. There's no any matching or pairing. Then we need to compare separate two groups. This is what we are going to study in this chapter or this unit. So paired and independent sample study designs both collect data in two samples. But with per sample, each data point in the first sample is matched the unique data point in the second sample. But with, again, independent sample, the data points in the two samples are unrelated. So I may have two samples. One sample will be, size will be 20. The second sample size will be 12 or 10, any amount, because they are unrelated. So that's the independent sample. dependent sample or pair sample, the size must be the same. I have a golf club. I play, it's new. I use it today, I use it tomorrow. I collect two different values or two different data. I will pair them together. So that's a pair sample or dependent. So overall, this is what we're going to cover: a quantitative outcome in a test. We may have one sample, and that's what we cover in our previous lectures. Then also we may have two samples. In the two sample types, we may have the pair samples and independent sample. Again, we covered the pair sample in our previous lectures also. This is our unit 12 or chapter 12, where we're going to cover the independent sample. Again, the steps for the hypothesis testing is the same, but we may see again different formula and also different process, since again the data size may be different. Two samples may have a different data size, but with pair samples, the data size is the same. Actually, each value in each sample uniquely paired to another value in the other sample. So what type of sample? Here they say what type of sample? Let's say our examples here. The first one says measured vitamin content in loaves of bread and see if the average meets national standards. Here I would say it's a single sample because again, we don't have any two, we are not only one vitamin content in loaves of bread, so one sample. Compare vitamin content of bread loaves immediately after baking versus values in the same loaf 3 days later. So this will be dependent sample or the term pair sample. You can see that it's the same bread. We collect the vitamin content of it, then we wait after 3 days, collect the vitamin content data of it. This is the same as the golf club. I use it today, it's new, tomorrow is old, I use it again, compare the two data. So I may have a pair, again, sample or dependent. Then next is compare vitamin content of bread immediately after baking versus the loaves that have been on the shelf for 3 days. So here I'm different bread. A new bread that I baked today plus the bread that I baked 3 days ago. So again, this is independent sample. So the result is in the next slide. So as you said, the first one is a single sample. The second will be the pair sample. And the third is again, independent samples. And we have another example here. We said cholesterol and type A and B personality. So our question is, do fasting cholesterol level differ in type A and also type B personality men? So here we're going to collect the data. The data will be collected to get the level of the cholesterol level for type A and type B. We group them. Type A will be in group 1, type B will be in group 2. So we have their data set here. Again, each value represents the cholesterol level for type A, that's group 1, and each value for group 2 is type B personality cholesterol level. So this is again independent sample. Now, if we want to analyze this, we are going to use the SPSS data table. So we said one column for the response variable, then another column for explanatory variable, the group. So that's why we are using the response variable for first one. So based on the cholesterol level, we want to find there's a relationship between cholesterol level and type A and type B personality. Group 1 is type A, group 2 is type B. So that means the cholesterol level will be our independent variable and then the group will be dependent. So we use the term response, opposite with the response variable and also explanatory variable. So the next is to do our exploratory. The EDA stands for exploratory data analysis. We do this a lot in data mining, data science. Exploratory data analysis makes us to understand our data. For example, we can compare the mean, the spread of the data, the position of the data, 25%, 50%, 75% will be the quartiles, 1, 2, and 3. So we start with exploratory data analysis. Here we're going to compare the group shapes. We want to see the distribution of both group A, which is, group 1, which is the A personality, group 2 is B personality, they are cross-story level. We see how the data is distributed. Distribution shape can be normal shape, or it can be skewed to the right or skewed to the left, or bimodal, etc. So we can see here we are using the stem and leaf plot, and we can see the distribution. So group 2 is on the right side. Group 2 look almost like skewed to the right, and group 1 look like a normal curve. We have a thin tail for both sides, 3 and 2 here. So here we say the example of applicable techniques. We use a side-by-side stem plot. Again, the distribution, we can use so many techniques. We can plot the graph separately, but we decided to use the stem plot. Then we can also use side-by-side box plot. Side-by-side box plot is very good because it can give us the position of the 25%, 50%, 75%. And also we can see the spread and the difference also. And actually, I prefer the box plot because it's more accurate since it's calculations. Stem plot is kind of more like a graph. So here we can see it's a graph, but again, we use a formula to find the Q. Q1 will be the beginning of the box. Q2, which is same as the media, will be the bar in the middle, and the Q3, 75%. So just by looking at group 1 and group 2, I can say, okay, group 1 mean is very big because it's at the top. The mean corresponding for group 1 is high. But I also say that group 1 variance or spread, standard deviation, the spread is small because the box is very small. So the data, the difference between the data values are very close. But when we look at group 2, the mean is small, lesser than group 1, but the spread of the data is very wide. We can see how large is the box. So the box plot, by the largeness of it, will tell us how the data spread, the size of the box. So we say the side-by-side box plot location, which will be, again, the mean. So we say group 1 is greater than group 2, as we said that. The spread, we see that the group 1 box is very small. So the spread will be lesser for group 1 than group 2. But both fairly symmetrical. Outside values in each, no major departure from normality. And there's also no any outline in the data. So that's the summary statistics for the group 1 and 2. The sample size are the same, but the mean is different. Standard deviation also is different. As we said earlier, the standard deviation for group 1 is lesser than the standard deviation of group 2, based on the box plot. Now the inference about the mean difference notation, these are some of the notation we're going to use. When we are talking about the parameters, which is the population, we can know the population size is uppercase N1 and N2 for the group 2. The mean will be mu1 and mu2, and standard deviation will be sigma 1 and 2. Then for the statistics, which is the sample size is lowercase N1, lowercase N2. The sample mean for group 1 and 2 will be X1 bar, S2 bar. Then the standard deviation will be S1 and S2. Now, when we are dealing with two, we are comparing two means, that is, we have two samples. We also can find the point estimate. So the difference of S1 bar, which is the sample mean, and the sample mean 2, the difference of the two samples mean, will be the point estimator for the difference of the population mean for population 1 and 2. So to find the standard error for the mean difference, here we are using two independent samples. How precise is the difference of the sample mean as an estimator of the difference of population, the two population mean? So the standard error of the mean difference will be square root of S1 square, which is the sample 1 variance, divided by sample 1 size plus sample 2 variance divided by sample 2 size, square root. And that will give us the standard error of mean difference sample. So here we say there are two ways to estimate the degree of freedom for this standard error. So degree of freedom for wedge, this is an example. Let's say we're looking for degree of freedom for wedge set. We can use the formula, which we saw previously, use the formula, or we can use the calculator to calculate it. Now, degree of freedom for conservative, that's if the data is smaller. Let's we say the smaller of n1 minus 1 or n2 minus 1. For the cursory comparison data, the standard error again will be the, as we said, the variance of the first sample. So here we know the standard deviation of the first sample, so we square it, divided by the sample size plus the standard deviation of the second sample divided by sample size. Square root, we get 13.563. And the degree of freedom, if we use the SPSS, we get 35.4. Now the degree of freedom for conservative, we say the smaller of n1 minus 1 or n2 minus 1. Since n1 and n2 are 20/20, then degree of freedom will be 90, 20 minus 1. We also can find the confidence interval for the difference of the population mean for first population, second population. So when the time we're looking for confidence interval, alpha will be given to us. If alpha is 5%, then the confidence interval will be 95%. So here we say 1 minus alpha 100% confidence interval for the difference of mu1 and mu2 is equal to the sample x1 mean and s2 mean. So this will be the difference of sample mean of the two samples, plus or minus t degree of freedom and 1 minus alpha over 2 times standard error, the difference of the sample mean 1 and sample mean 2. So we can see that this formula is almost the same as the paired when we were using the paired sample or even a single sample also. So for cursory comparison data, let's say we have SE, the difference of sample 1 and 2 mean is 13.563. Degree of freedom for conservative is 19. This is per slide. We saw 20 minus 1. So if I know the SE for D and I know degree of freedom, then we can find the confidence interval. So the confidence interval will be the difference of the sample mean 1 and 2 plus or minus T, degree of freedom is 19, 1 minus alpha over 2 is 0.975, which means the alpha is again 5%. So we plug in the values, we have the first sample mean minus the second sample mean plus or minus. We go to the T table, We go to the row 19, degree of freedom. Then we look the column for 0.975 P, and that will give us 2.093. Then we multiply by the standard error, which we already calculated to be 13.563. So when we do our calculation finish, we get 34.75 plus or minus 28.38. So the range will be from 6.4 to 63.1, because it will be 34.75 minus 28.38 to 37.75 plus 28.38. So that will give us the range. So here we can say we have 95% confidence interval, because the alpha value was again 5%. That the confidence interval for the mean, population mean, will be between 6.4 to 63.1. So these are the comparison of confidence interval formulas. Type of sample, we use the single sample. The point estimate will be only the X bar. Degree of freedom for T is n-1. And the standard error will be S divided by square root of n. We use this again at the beginning in unit 11. Then when we have the paired, we have to find a pair means we have at least two samples. We find the first sample mean, the second sample mean, then you find the difference. So this will be the S bar D, the difference of the two sample mean. Degree of freedom is the same as single, n-1. And then the standard error will be SD divided by square root of sample size. Now, if your data or your sample is independent, then the point estimate will be the difference of the first and second sample mean. To find the degree of freedom, we take the smaller of n1 minus 1 or n2 minus 1. And to find the standard error, we said is the variance over n1, the first sample variance over n1, plus the second sample variance over the second sample size n2. So next we move to the hypothesis testing. And the process again is the same. First we state our hypothesis, the HO and HA. Then we do our test statistics. We find the p-value. We compare it to the significant level. And we make our final decision. So here we have two data sets, two different samples. We want to check if both mean, population mean is the same. So the claim here for null hypothesis will be, is mu1 equal to mu2 against mu1 not equal to mu2, which will be two-sided. Or we can say the alternative hypothesis also can be mu1 greater than mu2, which is right-sided, or mu1 is less than mu2, which is left-sided. So after we state our claim for HO and HA, we will go and look for the test statistics. So the test stat here will be the difference of the sample mean, the sample 1 mean, and sample 2 mean, the difference of the two, divided by the standard error for the difference of, again, sample 1 mean minus sample 2 mean. The standard error for the difference of sample 1 mean and sample 2 mean is a square root of the variance of the first sample divided by the size of the first sample, plus the variance of the second sample divided by the size, the sample size of the second. So when we get the T, we can find the P because we know the degree of freedom. So we have the degree of freedom, we have the T value, we can find the P. Now here we're going to say, okay, if the P is less than the significance level, then we are going to reject HO. Otherwise, again, we are going to accept HO if P is greater than or equal to the significance level, the alpha. So let's see the example. This is again continuation of our previous example. We have the values for the sample mean, the standard error, the degree of freedom is 20 minus 1, which was 19. So first we state our hypothesis testing. We say the mu1 is equal to mu2, then mu1 not equal to mu2, so we are doing two-tailed test. Next, we find our test static. We say in the prior analysis, we calculate the sample mean difference. It's 34.75, that's the sample mean difference. Then we know the standard error already, and we know the degree of freedom. So if that's the case, I can find the t-stat. The sample mean difference is 34.75. The standard error difference will be 13.563. So that gave me 2.56 with 19 degree of freedom. So with these two values, I can find the P. Now we go to the T table, go to the 19th row, look for 2.56 and go to the column top. We have our P to be, the P there maybe will be 0.01. But when you use a computer, you can get more precise value. Yes, 0.019. And now, since 0.019 is less than 0.05, we have a good evidence against the HO. We are going to reject HO. And the significance level against an optional, that is the evidence against HO is significant at alpha equal to 0.02, but not at alpha equal to 0.01, because 0.019 is greater than 0.01. So if we are using the SPSS, this will be our output. You can see the T value is 2.562. Degree of freedom was, we find it. We are doing two-tailed tests. We have 0.015. The mean difference was 34.75. The standard error difference was 13.563. And then the 95% confidence interval will be from 7.227 to 62.273. So next is the equivalence T procedure. This is an optional. Actually, this will lead us to ANOVA. ANOVA is analysis of variance. This is also the concept of analyzing variance. We want to find the equivalence T procedure. So this is also called the pool variance T procedure. And here we say that it's not as robust as the prior method, but it's historically very important. And it can also be calculated by using, again, a software program. And that, again, as we said earlier, it will lead us to advanced ANOVA techniques. So here, inferential comparison presented in the prior section made no assumption about whether the variance in underlying population were equal. Now, again, we present a procedure that does have this requirement. This procedure is called the equivalence T procedure or pool variance T procedure. And again, this may lead us to ANOVA. So doing the pool variance procedure, first we start by calculating the pool estimate of variance. And this is the formula. Here we have two independent samples. So it will be the degree of freedom for one times the variance of the first plus degree of freedom for second sample times the variance of the second sample divided by the sum of the two degree of freedom, where again S1 square, S2 square are the variance for sample 1 and sample 2. Now with the pool variance, we use the formula below to find the standard error of the difference, which is square root of variance that is pool multiplied by 1 over N1 plus 1 over N2. N1 and N2 again are the two sample sizes of the independent. Now, if I want to find the confidence interval, it will be the difference of the sample mean plus or minus t degree of freedom and 1 minus alpha over 2 times SE delta. So we can see that the formula here is almost the same as using the pair sample or two dependent sample and two independent sample. The formula is the same. Now with the test statistics, it's the difference of the two sample mean divided by the standard error of delta, the difference of the two sample mean. Now, all with the degree of freedom, df1 plus df2 is equal to n1 minus 1 plus n2 minus 1. So the pool variance confidence interval, we'll do our calculations, and we may come up with this. So we have two groups, 1 and 2, the size is the same. We know the standard deviation for both of them, and also we know the X bar or the X mean. So here we can find the standard error for the difference. Then we find the degree of freedom. Then we can find a 95% confidence interval, which means here will be 238 and 0.975 because you get 1 minus 0.05 over 2. Because we're using 5% for alpha because it's 95% confidence interval. So we plug in all the value. This is the interval we get from 7.36 to 62.14. We are 95% confidence. So this is the pool variance t-test. So we have the group 1 and 2, the sample size, the standard deviation, the sample mean. We can also find the standard error for the delta, plug in the values, degree of freedom 20 minus 1 plus 20 minus 1. Then our HO, we say the mu1 is equal to mu2. We find our t-stat using the formula. We find our degree of freedom. With the degree of freedom and t-stat value, we can find the P. The P is 0.015. So these are some of the conditions for inference. The condition required for T procedure, validity condition, very important. We must have a good information. There's no any bias in the information. We also must have a good sample. The selection process, there shouldn't be any bias. Also, we don't need a confounding variable. Confounding variable, again, are the variable that shows that there's a relationship, but actually there's no causation, but there can be a relationship. Then sampling condition, independency, normal sampling distribution, which we cover in unit 9 and also unit 11. So this will be the conclusion of, again, our unit 12, which is comparing independent means. So in these lectures, again, we went through what is an independent sample and the concept of a pair sample, which is the same as dependent sample. Also, we discussed how we can do the hypothesis testing for, again, two independent samples. And again, wish everybody the best and see you in the next lectures, which will be unit 13. In unit 13, we're going to learn the ANOVA, that's analysis of variance. So wish you the best. Thank you.